In this video, we'll talk about the nth term divergence test, which provides our first way to figure out if a series converges or diverges without actually computing the partial sums or the number that it would converge to. There's going to be a theme going forward in this chapter is deciding if series converge or diverge without being able to actually evaluate them. Like for a lot of integrals, you can't really evaluate them. You don't really know what's going on, but you want to determine if they converge or diverge, what they do. The same thing is here for series. There are lots of series that we want to know if they converge or how they converge, but they are too complicated for us to evaluate by hand. And this is also where numerics come into play, because if you know it converges, you know if you take enough terms, you'll be close to the answer, and you can use that to approximate the value of the series. So here's our first test determining convergence or divergence of series without being able to evaluate their number directly, and that's the nth term divergence test. And what this says is pretty simple. This says if the terms of the series, so this an, does not converge to 0, then the series of this an diverges. So if the terms don't go to 0, the series must diverge. So this provides, for instance, an easy way to say that the sum from n equals 2 to infinity of n over 4 plus n diverges. Why? If I take the limit of that thing inside the sum, that goes to 1, which is not 0, and therefore the series diverges. However, this test says nothing about if a series converges, right? You can never get a result that says, therefore this series converges from this test, hence why we call it the divergence test. This can never tell you that a series converges, only that it diverges, right? Just because the terms go to 0 doesn't mean that it converges, but the terms not going to 0 means that it must diverge. So to put that all in perspective, let's look at an example. And this I have titled non-example for a particular reason. I want to investigate the sum for n equals 1 to infinity of 1 over square root of n. So we'll notice here that my terms, an, are 1 over square root of n, and so the limit as n goes to infinity of an equals 0. So if you were applying that divergence test incorrectly, you would say that therefore this series converges, which is wrong. Because just because the terms go to 0 does not mean it converges. If I had gotten something non-zero here, I could conclude that it diverged. But because I got 0 here, the divergence test tells me nothing. So what can we say about this series? Well, let's look at the partial sums. So the partial sum is going to look like a 1 plus a 1 over root 2 plus a 1 over root 3 plus a 1 over root 4, which is 2, but I'll leave it that way, plus a 1 over square root of n. Now, what can I do here to make this look nicer? This is a trick, and it's a trick that you have not probably seen before, but once you see it a couple times, you'll see sort of where it comes from, and you might be able to spot when you can use it if it comes up in the future. So this sum here is bigger than if I replace every term in it by the last one, because these terms are getting smaller. It's bigger than if I write this as 1 over root n plus a 1 over root n plus a 1 over root n, because I've only made each term smaller by replacing 1 by 1 over root n, I made it smaller. By replacing 1 over root 2 by 1 over root n, I made it smaller, and so on down the line. Now, there are n terms here. So this is the same thing as n over root n, which is square root of n. So what this then tells me is that my partial sums are bigger than the square root of n, which means that this must go to infinity as n goes to infinity, because square root of n also goes to infinity. Therefore, since these partial sums go to infinity, they do not have a limit, they do not converge to a number, this series diverges. So this provides one example of a series whose terms go to 0, but the series itself diverges. The divergence test only goes in one direction. It only says if the terms do not go to 0, then my series must diverge. It says nothing if the terms go to 0. So you have to be careful when you're trying to analyze series, especially with the tests we'll do in the next couple sections that have both convergence and divergence results. This one here does not. This one only gives me divergence. It can never give me convergence. And it's important to keep that in mind as you're trying to analyze whether different series converge or diverge.